Okay, the second example they give is you have a charged rod of some kind, which I guess it's infinitely long because I don't see an end to it. So this is some center, which we define at that point right here. So I'll call it 0. And then we have our little differential element here. So it's going to have a length dl. And this distance from here to here is y. And then we have some point P that we'll say here is 0, but it doesn't really matter if it's an infinitely long thing because it's going to have as much distance on either side. So this is the distance. This is the middle point. And there's your point P. And so this has some charge. And for this particular dl, the line goes like that. And then I'm going to shrink it. So the electric field is in this direction. So this is my dE electric field vector, and there's going to be an x component. And there's going to be a y component. Well, this is the y component. That's the x component. This is the y component. So this is dE sub x, dE sub y. And you can see that if I move this down symmetrically down to here, you're still going to have an x component, but the y component is going to cancel out. I mean, you're still going to have a x component, but the y component cancels out. So just like in the previous example, all we have to worry about is the x component when we calculate the total electric field at that particular point. So the differential form of Coulomb's law for electric fields is the same thing. We have K, which is 1 over 4 pi epsilon 0 times dq over r squared. And again, dq, differential charge for this length, is going to be equal to the charge per unit length, lambda like we had before, times dy. Now we don't take total charge because we don't really, this is infinitely long, so theoretically, if it's infinitely long, it's going to have an infinite charge on it, but the charge per unit length is going to be finite. So just like we did before, you're going to have a triangle that's going to define this direction. So this is r, this is x, and this is y. So we know from the Pythagorean theorem that x squared plus y squared equals r squared. So we can go ahead and plug in for r squared. We can put in x squared plus y squared. And for dq, we'll put in lambda dy, and that's divided by x squared plus y squared. And we're going to integrate that with respect to y. The x component is just going to be the let's see, x is, this is theta. So just like before, the differential x component is the cosine of theta times dE. The y's cancel out, so the total electric field is the integral of the dx components, dE sub x, which is equal to the integral of the cosine of theta times dE. Remember, the cosine of theta is okay, so we're going to have something slightly different here as far as how we deal with this cosine of theta thing. Why is that? Well, let's see here. So let's go ahead and put this in. So we'll have cosine of theta times dE, which is this. So we go 4 pi epsilon 0 times lambda dy over x squared plus y squared. So we can take out the constants. Lambda is a constant for a given problem. 4 pi epsilon 0 is a constant. We integrate cosine of theta divided by x squared plus y squared dy. So I'm just going to stop for a second and think about this. Okay, so the theory here is that we could integrate from negative infinity to positive infinity as far as y is concerned, or we could do the integration with respect to theta. So if we look at this, so when you get out to y equals positive infinity, theta goes to 0. So as y goes to positive infinity, as y goes to positive infinity, theta goes to positive pi over 2, and y goes to negative infinity, then theta goes to negative pi over 2. So instead of the limits being infinite, we can make the limits finite. Now, I think you could still do it if you did it with respect to y, but I think that's why they do that in the book. So if we look at the geometry of the situation here, we can see that in terms of x and y, that y, well, we can see that the tangent of theta is the opposite over the adjacent. So y is equal to x times the tangent of theta. And if you take the derivative of this dy, or the differential, this is a constant, and the derivative of the tangent is going to be equal to the secant squared. So you get x secant squared of theta times d theta. So you're using implicit differentiation there. So that's also equal to x d theta over cosine squared theta. So dy is equal to that. So what we can say is dy is equal to x, what did we say it was? X d theta over cosine squared. X d theta over cosine squared of theta. And we can also find out, what we need to do is replace this with something in terms of theta. So this, let me just write it here. So this is r, this is x, this is y. So what we do is we see that the cosine of theta is equal to the adjacent over the hypotenuse. And r in terms of x and y is x squared plus y squared, square root. So if we square both of these, we get the cosine squared of theta is equal to x squared over x squared plus y squared. Therefore, x squared plus y squared is equal to x squared divided by the cosine squared of theta. So we plug all these things into here, you get the cosine of theta times dy, which is x d theta divided by the cosine squared of theta. And then you divide by this, which is the cosine. You take the reciprocal of that because it's 1 over x squared plus y squared. So you take the reciprocal of that, you get cosine squared theta over x squared. So you see these two cancel out. This cancels out with one of those. So we end up with the cosine of theta d theta over x. So going back here, so we're changing the variables. We also have to change the limits. So limits of integration. So this whole thing becomes cosine of theta d theta over x. The x can be brought out because it's a constant in this particular case. It's distance from the, and the limits are from negative pi over 2 to positive pi over 2 of the cosine of theta d theta. Well, the integral of the cosine is the sine. So we get the sine of theta evaluated between negative pi over 2 and positive pi over 2. So if you remember, the sine is the y component, is the y, so we go from y equals minus 1 to positive 1. So our limits, our result, the sine of pi is 1, and the sine of negative pi over, pardon me, the sine of pi over 2 is 1, and the sine of negative pi over 2 is negative 1. So we'll get 4 pi epsilon 0 x times 1 minus a minus 1, which is 2, so you get 2 times lambda over 4 pi epsilon 0 x, and you see that simplifies down to lambda over 2 pi epsilon 0 times 1 over x. Yeah, the book actually has 1 over 2 pi epsilon 0 times lambda over x. And that is the total electric field at this point, P, the distance x, from this charged